Let's go ahead and get started. Welcome to class. Today is February the 27th. Does that sound right? This is actually a very important day in my life because it's my half birthday. I'm 43 and a half. I'm 27 and a half. Oh, how would it be to be 27 and a half again? What do they call that? A golden half birthday? So we have the topic of hypothesis testing for this week, and that's the Chapter 9 material. And hypothesis testing is just another way to do statistical inference. And it turns out that if you do it right, hypothesis testing is really the same thing as confidence intervals. So a little more in depth, a little bit more computation that you have to do, or maybe, I don't know, the thought process is maybe a little bit more complex, but it's really the same thing. And I'll try and help you see that as we go. So what's a hypothesis? And before we jump into this, I will be asking or entertaining questions from homework that's due this week. I think it's homework number 6. Is that right? Anybody know? Homework 6 due this week. And we have homework 7 due next week. Homework 8 due the following week. And there are only 2 more quizzes. Quiz 6 and 7. There is no quiz 8. And then the final exam, I believe, has been scheduled for the Tuesday of final exams week. It's the 21st, 20th, 21st, whatever that is. 21st, I think. 20, I don't know, whatever it is, whatever they've got it posted as. And so I do have computer labs scheduled for that. So it will be very similar to the midterm exam. Okay, so we got that out of the way. What's a hypothesis? Anybody ever do the science fair when you were in elementary school?
It's like an explanation made on
Okay, so it's that's a fine definition. I think, if I remember correctly, back to when I did the science fair. Did I do the science fair? I don't know. My kids did the science fair, and they said a hypothesis is an educated guess. Right? So you've got some sort of evidence that is the education part of that, but really it's just a guess. So when we're going to do hypothesis testing, we have 2 different hypotheses. The first one's called the null hypothesis, and the other one's called the alternative. And sometimes this is written as H1, sometimes it's written as HA. I don't remember what this textbook uses. And either one of these is true, but they both are not true at the same time. So think about some hypothesis that so this is what's used in science. This is kind of the basis of scientific thought and discovery. And we're actually going to do a really fun and exciting hypothesis test in just a minute. So I hope you can contain the excitement. I know statistics can be boring. I was actually going to be an accountant, but I couldn't handle the excitement, so I became a statistician. And so there you go. There's the statistics joke for today. So when we have an educated guess, that's usually going to be the alternative hypothesis that we're testing. So what's an example of a hypothesis test? A very famous one. Happened, I don't know, in the 1400s, 1500s, something like that. Everybody thought that the Earth was flat, right? And it was on the back of a giant turtle, and it was turtles all the way down. And at the heart of the matter, that's really the explanation that is used for a lot of things that we just don't understand. But why did people think the Earth was flat? I mean, of course, there's mountains and hills and that sort of thing, but why do they think it was flat? Because if you stand on the ocean or on the beach and you look out at the ocean, it looks like it's pretty flat, doesn't it? Right? And water is where everything's kind of leveled. And so that was the idea, that Earth is flat. And so that would be the null hypothesis. This is the business as usual hypothesis.
So it's like something's true because it hasn't been proven false.
That's kind of the idea, yeah. But, I mean, I wouldn't think of it just like that. Why did people think the Earth is flat? Well, I don't know, but everybody believed it. And that was just kind of the common school of thought. So whatever the current school of thought is, give the benefit of the doubt, don't rock the boat. There's got to be a few more cliches like that you can think of. But that's really what the null hypothesis is saying. Whatever everybody is currently believing, well, okay, we'll go with that. And why? Because if you say something like the Earth rotates around the sun instead of the sun rotating around the Earth, it can get you killed. Just ask Copernicus. Or was it Copernicus? Yeah, it was Copernicus. So everybody used to think the Earth was flat, and they had good reason, and it's just how it was. And then someone came along and said, I don't think the Earth is flat. I think it's round. And so the burden of proof is on the alternative hypothesis. So the guy who came along and said, I think the Earth is round, he has to prove that. He has to convince everybody else that that's the case. So what kind of evidence did he have? Well, about the time that telescopes were invented, so this is like when Galileo was alive, somebody decided, I'm going to watch this boat go out to sea. My family's on it, or the father of the family's on it, so let's take the kids out and watch this boat go out to sea and just see how, what happens way out there. And it should just be a speck that gets smaller and smaller and smaller, right? Because it's flat, so you should still be able to see it. But what happens when the boat gets pretty far out there, starts going over the curvature of the Earth? Looks like the boat has taken on some water. And it keeps taking on water the further it goes out, and it looks like the boat sinks. So you got this whole town full of people, and all of their, the men from all the sailors from the town, they're in a boat that sank, way out there. There's no way they can get out there in time to save them. So they have like a mass funeral service and memorial and all this stuff, and everybody wears black for a couple of months, and it's very traumatic. And then they start moving on with their lives, and then what happens? The ship comes back, right? Because it didn't really sink. So that's the evidence that we're looking for that says, oh, maybe the Earth isn't flat, it's actually round. And then, depending on who you ask today, I think Kyrie Irving still thinks it's flat, or at least he made some post, some statement about everybody thinking the Earth's not flat just because, I don't know. Anyway, pictures from space show that the Earth is not round, is it? It's actually kind of, it's roundish, but it's not a ball. It's spinning on an axis, so it's like a squish ball. It's like a spinning racquetball. If you've ever seen one of those spinning really fast, they kind of elongate. But the point is then that we're going to use the same idea to test the value of a parameter. So our null hypothesis is going to be that mu is equal to mu 0, or if we're talking about a proportion, we would say pi is equal to some value of pi that for some reason we think we know. So maybe it's already established in industry that the average foot size for females is some size, and That's based on years and years and years of making shoes and selling shoes and measuring feet. That's the null hypothesis. So we're going to go with that. Unless, what? Unless we have evidence that contradicts that. Okay? So the null hypothesis is that mu is equal to some value, mu 0. The alternative is that it's not equal to mu 0. And same thing with the proportions. We can say what's the probability of success, or the proportion, population proportion. It's either pi 0 or it's not pi 0. The mean is either mu 0 or it's not mu 0. Okay, so this is what we call a two-tailed test. It's possible to have a one-tailed test if you have the null hypothesis that says that mu is greater than or equal to mu 0. Then the alternative is going to say that mu is less than mu 0. And same thing here. And you can go the other way for a, so this first one would be a right-tailed test, left-tailed test, and you can have a right-tailed test going the other way as well. So the question that we want to ask ourselves is, should we reject the null hypothesis and conclude that the alternative is true, or should we stay with the null hypothesis? And the data that we collect is going to tell us if we're going to do that. And so how do we do this? We're going to, first of all, need a test statistic. And we have, for mu, if we're testing for mu, our test statistic is going to be x bar. If we're testing for pi, our test statistic is going to be p. And we're going to say, did the value that we observed, x bar or p, if the null hypothesis is true, how likely is it that we saw that value? So in other words, what do we know about the distribution of x bar? It's got a mean with, it's normal with a mean of mu 0 and standard deviation sigma over the square root of n if what? If the null hypothesis is true. Right? The null hypothesis says that mu is equal to mu 0. So if the null hypothesis is true, that's what the distribution of x bar looks like. And we can draw that picture, can't we? Here's mu 0. That's what we are hypothesizing. And so when we take a sample of x bar, we want to say how likely is the sample that we observed. And what we really want to know is how big is the difference between x bar, let's say we get this value of x bar, how big is the difference between x bar and mu 0? And if the difference is big, then we're going to say probably the null hypothesis is not true. And if the difference is small, we're going to say probably the null hypothesis is true. In other words, we know that we've got this normal distribution and there's some randomness, some random variation. So if x bar is not exactly equal to mu 0, and it almost certainly will not be, we have to answer the question, where did the difference come from? Is it due to randomness, in which case the null hypothesis is still true, or is it due to the fact that the null hypothesis is not true? So really what we're doing here is we're making a decision, and the decision is going to be based on what we call a rejection region, or in this case 2 rejection regions. And let me just write down the distribution for p. P is also normal with a mean of pi 0 and a standard deviation, which is the square root of pi 0 times 1 minus pi 0 over n. So again, if the null hypothesis is true, then we have this picture. Let's call that pi 0, because these are both normal, and there's our sample value of p. So what we're going to do with hypothesis testing is that we've got to make a decision, and we're going to just draw a line in the sand. And if that line gets crossed, we're going to reject the null hypothesis. In fact, we're going to draw two lines in the sand if we have a two-tailed test. In other words, we have a rejection region up here and a rejection region down here. Now, have you ever drawn a line in the sand, like on the playground with your friends? What's the null hypothesis when you do that? You're betting that they're not going to cross that line. And if they cross the line, then what happens? Then you're going to go to town on each other. And it's going to be painful, and someone's going to probably get hurt, and it's going to be a mess because you got to explain it to your parents or your teacher or whoever it is, the police, come and arrest you for it. So the null hypothesis is the hypothesis that says business as usual, there's nothing to get worked up about, there's no action to take. And that's why we call it the null hypothesis. The alternative hypothesis, that's the one that says, okay, you cross the line, let's go. Let's put on the gloves, or let's take off the gloves, and it's going to be painful. Same thing's true in a business process. You have a machine that is making screws, so you can bolt something to a component that comes in from somewhere else in your factory, and the machine's supposed to make the screws in a certain specification. And if the machine's working, then you just take the screws and you do what you need to do. So the null hypothesis is that you spend a lot of time buying the machine, setting up the machine, running the machine. The null hypothesis is that the machine is working correctly. The alternative hypothesis is that it's not working correctly. So same thing. You cross that line, okay, we got to shut down the process. We've got to stop everything that's going on, and we've got to fix the machine. It's painful, it's time-consuming, it's expensive, it fouls everything up. So we don't want that to happen. So we want to be sure, as sure as possible, about rejecting the null hypothesis when we should. And so this rejection region is going to have a certain probability affixed to it. And we would say the probability of rejecting the null hypothesis when it's true is alpha. So alpha is the probability of rejecting H0 when it is true. And it turns out this is the same alpha that we used with the confidence intervals. So 1 minus alpha was the confidence level. We talked about that last week. But alpha is just the probability of rejecting the null hypothesis when it's true. This actually has a name. This is the probability of a type 1 error. So notice it's not a type 1 error. It's the probability of a type 1 error. So a type 1 error is one in which we reject the null hypothesis when we shouldn't. In other words, you got to make a decision. And there's exactly two states of nature. One is that H0 is true, and the other is H0 is false. And it's your job to either reject H0 or not reject. And we're always going to think about this in terms of the null hypothesis. So if we reject H0, what we're saying is we don't think H0 is true. If we don't reject H0, really what we're saying is H0 might be true, it might not be true, but I don't have evidence that tells me to reject it. So we'll just go with it for now, and if evidence shows up later that says we should reject it, we will reject it. So if H0 is true, what's the correct decision? I mean, you've got to decide, are we going to reject or not reject? That's your job. You're the analyst. You're the one who was hired to do this. You look at the data. Correct thing to do if H0 is true is to not reject it. So we'll say that's the correct decision. If H0 is false, what's the correct thing to do? We should reject it. Right? So there's two ways in which we can make the right decision, and that means there's two ways that we can make the wrong decision. If H0 is true and we reject it, I just told you that this is a type 1 error, and the probability is alpha doing that. So what do you think the other one's called? The null hypothesis is false, and you don't reject it. That's a type 2 error. And what's the probability of that? It's called beta. Okay, so what's the probability of making the correct decision when the alternative hypothesis is true? That's what I'm asking for, is something called the power. And that's 1 minus beta. So which of these correct decisions represents making the correct decision when the alternative is true? Or rather, which one of these has power as the probability? It's this one here. So the probability of making the correct decision when the alternative hypothesis is true, that means the null hypothesis is false. That's 1 minus beta, and that's what we call the power of the test. So the probability of this other one down here is 1 minus alpha. And as far as I know, that doesn't have a special name. But if you come back up here and look, we can see what's going on here. Our rejection region is determined by the alpha level, and that gives us a critical value. In this case, we have 2 critical values. So we would take our test statistic, which is going to be x bar, right? X bar right here, and say, is it in the rejection region? Is it over the line? Did it cross the line? If it did, then we reject the null hypothesis. If it's in the non-rejection region, then we're not going to reject the null hypothesis. Okay, so what's the correct thing to do? That depends on what? Correct thing to do is to not make a mistake. Depends on if the null hypothesis is true or not. Do we ever know if it's true or not? No, we can't ever know for sure. Can we? Question, go.
Test it, like try to test it. Could you test the formula to see if it works?
Well, that's exactly what we're doing. And my point is that when we run this test, we can't be 100% sure we're making the right decision. Why? Because alpha is the probability of making a type 1 error. And what would it mean if alpha were equal to 0? I mean, we have no rejection region, right? If I said take this area right here, alpha over 2, and shrink that down to 0, where does that put my critical value? It puts my critical value at infinity. So the only way to be absolutely sure is to get rid of the rejection region. And that doesn't really do us any good. So, so let's add in, let me draw the picture again on the next page. Let's add the power mix. And let's do this with a null hypothesis that says mu is less than or equal to mu 0 versus the alternative that mu is greater than mu 0. So I have mu 0 right here. And if I have, so this is called a right tail test. The null hypothesis says the mean is less than or equal to some number. So if I get my X bar, which is my test statistic, and it's down here, let's say, that's evidence in favor of the null hypothesis, because the null hypothesis is saying the mean's either mu0 or less. So I'm going to have a rejection region that's in the right tail only. And this area here is going to be alpha. Okay? So if the alternative hypothesis is true, let's change the color. If the alternative hypothesis is true, we'll just write it as mu1 is the true value. It's bigger than mu0. Okay? So if that's true, I'm still going to have this normal distribution. It's just going to be centered at mu0 instead of mu1. And let me draw that a little bit different. Okay, so the rejection region doesn't change. That's determined by alpha and the null hypothesis. So the question is, what's the power of the test if I know what mu1 is? And this is all hypothetical because I don't know what I don't know, first of all, if the null hypothesis is true or the alternative is true. And if I do know the alternative is true, I certainly don't know what the true value of the parameter is. So the way this works is you'd say, okay, hypothetically, what if mu was mu1? So you pick a number, plug it in, and then you would say, well, the power of the test is going to be 1 minus beta. Well, what's beta? Beta, remember, is the probability of making a type 2 error, which says the alternative is true, but what? But we don't reject the null, which means under this blue distribution, we have the area under the curve in the non-rejection region. So that's beta, which means the power is the probability of being in the rejection region under the alternative hypothesis. Okay, so if we know what mu is, if we know what alpha is, and we know what our sample size n is, then we can calculate the power. So alpha, beta, and n are all variables that go into this, and if I know any two of those, then I know the third one. And so oftentimes we will say, give me alpha, give me beta, fix those things, and then that will tell me how big my sample size needs to be in order to have the power that I want. Okay, and so you could change this value, use 0, move it out if you want. If you do, that's going to change your power. It's going to change the beta. And so power curves are calculated by saying, okay, let's just look at the alternative hypothesis as if it's true, put in different values for the parameter, and that's going to give us different powers, and we can see how big the difference is between mu0 and mu1 before we're going to start to get a powerful test. In other words, there's a practical difference, and then there's a statistically significant difference. So if I want to know the proportion of students that, I don't know, what's something you guys are interested in? You want to know what your fellow students think about. Do you like Trump? Okay, so we could say, you know, I don't have any idea. It's 50-50. Let's just say the null hypothesis is that half of you, 50% of you, like Trump, and the other 50% don't. Okay, so I could go in and I'd say, well, here's 50%. That's my null hypothesis. And if I want a high-powered test to be able to differentiate between a small difference, right? In other words, if this is 51% or 50% and that's 51%, I'm going to have a bigger sample in order to differentiate between 50 and 51%. Okay? So what's the difference between 50 and 51%? Is it practically a big difference? No. I mean, okay, so it's 51% instead of 50%. Now, sometimes 51% can make a big difference, but in this setting, in this example, you know, I don't care if it's 50 or 51%, it's about half. But what about the difference between 50 and, say, 60%? Is that a big difference? So the question we're asking ourselves is this a big difference? And do we want to be able to distinguish between the differences? In other words, if it's 60%, I'd like to be able to have a test that's powerful enough to pick that up. If it's only 51%, maybe I don't really care if I can differentiate between the difference between those things. So I would calculate the power as a function of mu1, let's say, or pi. All of a sudden we're talking about pi, so we'll say pi 0 and pi 1. So I would calculate the power as a function of pi 1 and say, okay, let's let pi 1 get big, or go from 51 up to 60%, and that's going to give me different values of power. And for a fixed sample size, if I'm trying to differentiate between 60% and 50%, that's going to be more powerful than if I'm just trying to differentiate between 50 and 51%. Okay, so that's this notion of power. I think I asked you in one of the homework questions to actually calculate power, and so you would say we'll do that. We'll do that in our example in just a minute. Okay, so questions about this? Thoughts about this? Have you ever run into this situation before? Well, if you've ever watched Law and Order or one of these detective shows on TV where they go to trial, and at least in the American justice system, you've seen this, right? What's the null hypothesis when somebody's arrested and they're brought before the jury? What do they tell the jury? Presume they are innocent, right? The null hypothesis says they're innocent. The alternative hypothesis then is that they're guilty. They both can't be true. And so the jury hears all the evidence. It's the prosecuting attorney's job to bring evidence. The prosecutor wants to show that they're guilty. Now, this is not taken lightly because it's a lot of time and effort and resources that go into this sort of thing. So the prosecutors only bring cases to the court where they have evidence, and then it's their job to convince the jury that they're guilty beyond a reasonable doubt. So we can either convict. I should probably write that right here. Convict or acquit. And they're either innocent or they're guilty. All right, so if they're innocent, they should be acquitted. That's the correct decision. If they're guilty, they should be convicted. That's the correct decision. So type 1 error says we reject the null hypothesis when it's true. That's a type 1 error. So what does that mean? It means an innocent person goes to jail. Does that ever happen? Yeah, probably too much. That's a type 1 error. That means this is a type 2 error. And in practical terms, what does that mean? It means somebody who is guilty, they committed the crime, somehow they get off. Because the defense attorney pokes holes in all of the prosecution's arguments, and however they do that, we've got these two different types of errors. So a common thing to do in hypothesis testing is to look at the errors and determine how comfortable you are with making those types of errors. And unfortunately, you can't always, you can't say there's a zero probability of making any of these errors. There's always going to be a chance. So we can look at the cost of the errors, and that can be a guiding principle as to what to set those levels at. So what's the cost of a type 1 error? Well, so you've got somebody who's, say they're an upstanding member of society, they hold a job, they pay taxes, and you know, they're not a criminal. And so you take from the workforce taxes that they're paying, their contribution to the economy and so forth, and you erase that. You stick them in prison, and then you not only do you erase what they're paying into the system, now you're paying for their upkeep, their food, their shelter, their cable television, whatever it is they get in prison. So those costs can be measured, at least to some degree. And what about a type 2 error? How costly is that? Which one's more costly? Type 2 error says, okay, this guy is a criminal, and we're just going to put him back on the streets. You don't have to pay for his room and board. You don't have to pay for his cable television. He's out there doing whatever he is. He got away with it the first time, and maybe he's going to go back and kill more people or steal more money or whatever it is. So it's kind of hard to measure the cost sometimes, but those are the types of things that you have to do. And there's some people who argue that the type 1 error absolutely has to be avoided, and it should be, but it can't be entirely avoided. And so even at the cost of releasing criminals on the streets, there's of course other people who argue the other way. Let's keep the streets safe by locking up everybody, even if the evidence isn't that strong, and so forth. What other types of situations do you see this type of analysis being useful in? Anybody ever shop online? Anybody ever shop on eBay? That's like old school. Nobody. Okay, so a few of us. I bought a bike one time on eBay. It was beautiful. It was a Ellsworth Truth. It was like $4,000, and I got it for $600. So was that, what type of error do you think I made? Was that a type 1 or a type 2? I'll tell you right now, I made a mistake. Was it a type 1 or was it a type 2? That's a type 2. Why? Because they're advertising it for, I mean, the retail price was $4,000. They didn't have that on the listing. And this was before Safe Harbor and all that stuff that they instituted to make sure that you don't get ripped off. So I was out the $600, and I should have known better. And I've learned from the experience, and that's, I guess, another point to making decisions, is being able to learn from them. But I said, well, it's posted right here on eBay. They've got pictures of it. It looks like it's in good shape. And, you know, I was real excited about it. I'm going to finally get this bike after being in graduate school and whatever for years and years and years. And paid the money, and the bike never showed up. So my null hypothesis, and the null hypothesis they want you to use when you're shopping online, is that it's a legitimate transaction. Same thing happens when you get an email. Right? You get an email, okay, the null hypothesis should be this is legit. It's from somebody that I know. If I click on the links, it's not going to cause any harm to my computer or my life or my identity, anything like that. So in an online shopping situation, what's the cost of a type 2 error? This is a little easier to measure. Well, go ahead.
Loss of money.
Loss of money, right? I paid $600 for the bike. Never got the bike. Didn't get the money back. Cost me $600 for the type 2 error. what would the type 1 error cost me in that situation? Can I measure that?
The difference between the actual cost and price minus what you spent on the
Okay, so if a type 1 error in that situation is I say, wait a second, this looks like it's too good to be true, and so I'm just going to break the grip and walk away. And that's hard to do, I know. But if it had been a legitimate sell, then what does it cost me to buy the bike? If I pay full price for it, it's $4,000. So I don't pay $600. I still have my $600. But if I'm going to go out and buy the bike brand new, which of course I'm not going to, but that's $3,400 mistake. So you can look at these things, and I mean, it's an opportunity cost. I didn't really lose the money, but you can look at those things and make those determinations oftentimes. Okay, so here's the fun for today. I have this null hypothesis. I've been thinking about this for a while. My null hypothesis is that you guys, collectively, as a group, are not psychic. What do you guys think about that? Anybody know they are psychic? So as far as you know, as far as I know, you're not psychic. So if that's the null hypothesis, what's the alternative? That you are psychic. Okay, so how could we test this? You think of any clever ways that we might be able to test this hypothesis?
Ask someone to predict something.
Okay, we could ask somebody to predict something. Now, I did ask you guys to guess the secret serial number a while back, and no one was very good at that. But that was different, wasn't it? What if I mean, we need to collect some data. So what if we did this? What if I wrote down these numbers right here? And I said, all right, I'm going to think really hard about one of these numbers. And then I'm going to blank the screen so nobody can see what I'm doing up here. And I'm going to erase 3 of them. Okay, so just one of those numbers is going to be left. And I'm going to keep thinking about it. Just going to think, and I'm going to broadcast that out to everybody. And if you're psychic, you're going to catch up on, somehow you're going to tune into my brainwaves. And you don't necessarily know that you are tuning in when you're psychic, right? You just somehow it works out. So should we do that experiment? What do you guys think? That'd be fun? Yeah, it's totally fun. Let's do it. So I'm going to collect data from you guys with this thing. So I think if you just put in the number 1, 2, 3, or 4, it should show up here. And I've got it blocked so you can't see what everybody else is doing. All right, so let me just blank the screen for a second. You guys can't see what I'm doing up here. I'm going to erase one of these. I'm going to erase more than one of these things. Okay, you still can't see it, right? Okay. So bring the screen back up. Okay, so you have to put in A, B, C, or D. Nothing else is going to work. So A, B, C, or D. And I'm just thinking the number that I'm thinking about, and we've got 11 results so far. I really need everybody to tune in here. So there's 25 people here. We've got 17 responses. This should not be a hard thing. I mean, if you are psychic, it shouldn't be hard, right? You should have already gotten the signal. If you're struggling, I don't know if I should tell you to make your best guess or not, but submit something. Just bear down and concentrate. I mean, I'm broadcasting it out there. You should be able to pick this up. We've 4 more responses. $22. A couple more. Let's get a couple more. There's 23. And I guess we'll just go with 23. All right, so before I show you the results, let's come back over here. So I was thinking the number 3. And if the null hypothesis is true, that you're not psychic, how frequently should the number 3 turn up? 25% of the time. So we can rewrite this as pi is equal to 0.25. Now, is this going to be a one-tailed test or a two-tailed test? What do you think? In other words, the alternative hypothesis says it's not 25%, but if it's less than 25%, that doesn't really help us make the argument that you're psychic. So this is going to be, the alternative is going to be that pi is greater than 25%. So we're actually going to be doing a one-tailed procedure here. What if, sorry, say it again.
So what if, like, they are psychic, so they know it, and they pick a different.
Well, so yeah, you could poke all sorts of holes in this experiment, I guess. I'm trusting that you guys are, yeah, I mean, like, if you're trying to cover up the fact that you're psychic, you don't want people to know. You just want to use it for your own benefit and not have people harass you about helping them with psychic type endeavors. So I'm just going to trust you guys on this one. You did what you said you were going to do. Okay, so if the null hypothesis is true, then our sample proportion P should be normal with a mean of 25% and a standard deviation of 25% times 75% divided by, what do we have, 24, 23. 23. Oh, and I should probably lock that now so people aren't no one changed their response, did they? Because if you did, like to make me look bad, you could have done that. Because I can almost guarantee you we're gonna prove that you guys are psychic in just a minute here. Okay, so if we know this distribution, if the null hypothesis is true, we come down here and say, here's 25%. And if we're going to reject the null hypothesis, that means we've got a rejection region up here somewhere. So in other words, if we observe some number, some proportion that's bigger than 25%, that's going to suggest that the alternative hypothesis is true. But if it's just a little bit bigger than 25%, then we're going to say, yeah, it's just randomness. Because even if I had, you can think of this as a binomial random variable. If I had 25% chance of success and I ran the experiment 23 times, let's say we did it 20 times, I would expect to have 5 that were successes, but you know, I might get 6, I might get 7, I might get 8. So the question is there a statistically significant difference between what I expect and what I observe? And if it is statistically significant, that means I'm going to reject the null hypothesis, which is a different question from practical significance. Okay, and we kind of talked about that already. So what's the critical value here? What's the rejection region? It's going to be the value that has alpha percent of the area to the right of it. So it's going to be 0.25 plus 1.645 if, let's say, alpha is 5%. So from the normal table, we know 1.645 has 5% of the area to the right of it, times the square root of 0.25 times 0.75 over 23. I'm not sure what that is, so let's just pull up Excel so we can calculate that. Okay, so here we have pi 0, we'll call it. And here we have n. So we've got 0.25, n is 23. And so our critical value, first let's put in alpha, ALPHA. And then we have, so this is 5%, 0.05. Our z critical value is going to be equal to norm.s.inverse 1 minus alpha. So there's the 1.645. So our p critical value is going to be equal to p0 plus z times the square root of p0 times 1 minus p0 divided by n. So if we see a sample proportion bigger than 39.85%, 3985, if we see something bigger than that, that's going to say the difference between what we expect and what we observe is statistically significant. At the 5% level, we should reject the null hypothesis. Okay, so you guys ready for this? Everyone's ready for this? I haven't seen it, but let's take a look. Oh my goodness. Are you kidding me? 70% of you said 3. 70%, 0.7? Whoa. That's crazy. You guys are psychic. I mean, collectively. It's like this group wisdom. What do they call it? You know, they ask people to guess the weight of a steer at the county fair, and nobody gets it right. But if they average everybody's guesses, they're within like 3 pounds. It's amazing. It's like group consciousness or collective intelligence, group intelligence. Is that what's going on here? 70% of you got it right. So let's come back over here and say what did we observe? Let's change the color. We observed 70.7 right there. So what's the conclusion? Well, we're in the rejection region, aren't we? Oh, you missed the thunder. 70% of you guys got it right. 70%. Check this out. 70%. So we reject the null hypothesis because 70%, that's way the heck out there. And then what does that mean? I mean, if we say we reject the null hypothesis, people that understand statistics and this sort of hypothesis testing, they know what you mean, but not everybody does that, and even if they do, people want an explanation in terms of the context of the question. So in other words, what are you going to write home and tell your parents in an email this afternoon, or call them and tell them? Guess what? We have very, very highly significant evidence that my stat class is psychic as a whole. Now, it's too bad you can't take the exams together because, well, you only get 70%.
Can you go back to the Excel sheet? Here are the secret formula, please.
Yeah, so it's P0 plus Z. Oh, wait a second. That should be, so the critical values, okay, yeah. P0 plus Z times the square root of p0 times 1 minus p0 over n. Okay, so this is what we call the critical approach, or the critical value approach to hypothesis testing. And that's one way that we can determine if the difference is big. So we expected 25%, we saw 70%. Is that big? Yeah, it's big, but what does that mean? That means the rejection region is anything bigger than about 40%. So if we have anything bigger than 40%, we're going to reject the null hypothesis and conclude that we're psychic. You guys are psychic, according to how we set up this experiment. Okay, that's one way to do it. There's another way to do it, another way to calculate or determine whether you should reject the null hypothesis, and that is to find what's called the p-value. So the p-value says, what's the area under the curve further out than, or more extreme than what we observed. So we saw 70%. How could we be more extreme than that? Well, anything bigger than 70%. And what's the probability of that happening? That's the p-value. And we can compare the p-value to alpha. If the p-value is less than alpha, that means we're going to reject the null hypothesis. And that means the same thing, that the test stat in this case is bigger than the critical value when we're doing a right-tail test. If it's a left-tail test, then the reverse would be true. So our test statistic is 0.7, our critical value is 0.4, and alpha is 5%. So what's the p-value here? You guys know how to find the p-value? Yes, you do. How do you find the p-value? Well, we just have a normal distribution, mean of 25%. Standard deviation is whatever that number is. Square root of 25, square root of 0.25 times 0.75 divided by n. And the observed value is 70. So, or 70%, 0.7. So if we want to know the p-value, we have to first of all say, what's our value of p? It's 0.7. Actually, let's come back over here. 0.7 is big, but there might be some rounding going on here. All right, so we had 16 out of 23. So let's actually put that in. So x is 16, n is 23. And so p is going to be equal to x divided by n. So it's actually 69.56%. And so now we want to know what's the area under the curve to the right of this thing. So what's the probability of p-value? This is going to be what? What do we get? 1 minus norm dot s dot dist no, I could do it that way, but hold on. If I'm going to do it this way, I have to use norm.dist, and then I put in p, and then what's the mean? The mean is A2, right? I'm going to come back to this in a second. A2 is the mean. I didn't put in the standard deviation, so let me do that right now. Standard deviation of p is going to be equal to the square root of p times 1 minus p0 divided by n. All right, so I'm putting that in here so I don't have to type all that in again. And I could use that in this formula right here, but what I want to do is now edit this. Instead of A2, I want C2. That's the standard deviation, and I want this thing cumulative. All right, so C2, A2, C2, and so that's one way to do it. What's the other way to do it? we could calculate z. All right, what's z going to be equal to here? Z is equal to p minus pi 0 divided by pi 0 times 1 minus pi 0 over n, and then I've got the square root down there. So I can plug these numbers in. We get 16 out of 23 minus 0.25 divided by the square root of 0.25 times 0.75 over 23. And I'll just put that formula in here. This is going to be p minus a2, that's the mean, divided by c2, that's the standard deviation. So our z value is 4.9. So this is the p world and the z world. That goes to a 0 and that goes to 4.935. So 4.935. So what do we know about the z distribution, standard normal? Is that a big value, 4.9? That says 4.9 standard deviations above the mean. I've done this experiment many times, and I think in all but one we've rejected the null hypothesis, which means all but one of my classes is psychic. But I've never seen one this big, 4.9. So what's the probability of a standard normal random variable being bigger than 4.9 standard deviations? The empirical rule tells us that almost all the data is within plus or minus 3 standard deviations. The chart in the book only goes up to 3.5 or 3.7. So if we go all the way to 4.9, what we're saying is the probability is basically 0 of being bigger than that. And here's the p-value we already calculated. Another way to get this is 1 minus norm dot s dot dist, and then put the z in, comma 1. We get the same thing. So 4 times 10 to the minus 7. That's a whole bunch of zeros and then a 4. So it's basically 0. So we have overwhelming evidence that you guys are psychic. Which is pretty cool, huh? Do you think you're really psychic? No? Why not? If you publish this result in a scientific paper, people would be like, wow, that's amazing. You totally rejected that null hypothesis. And this is very rare to see something like this. And this is where you have to be careful with hypothesis testing, because guess what? You're not psychic. Sorry. Well, at least this test doesn't prove that you're psychic. I mean, because what does that mean? 70% of you are psychic, right? So which of you got it right? Well, 70% of you, but it turns out that there's a little known fact that if you have the numbers 1 to 4 and you ask people to randomly guess at them without telling them that you're being tested to be psychic, you say randomly guess, most of the time they pick 3. And I knew that in advance, so this was totally bogus. Which you have to be careful of, because sometimes you get results that, hey, this is great, but you have to go and look at the underlying experiment you're doing and the history and the background, and oftentimes you get yourselves into trouble by doing this, right? I mean, so you think you're psychic now. What are you going to do with those psychic powers that those of you that got it right? You're going to go invest in stocks. Well, which stocks are you going to pick? Oh, I'm psychic. I can figure out which one's going to go up tomorrow. Well, you can't. And I think we made an argument about randomness and uncertainty and that sort of thing previously. Although being psychic, if you really were, could overcome that, I suppose. But it's, power akin to time travel. And did I show you the video? How Spider-Man 2 should have ended? I didn't show you that. I know it's posted on the webpage, but did I show? Yeah, okay, I probably did. All right, so let's take a break. when we get back, let's start at 15 after. I will entertain questions from the homework, and then we'll take that as long as you want, and then we'll be done.
Can you call me at top of the hour?
That's actually the wrong homework assignment. The right one. Okay, so number 4, was that the first one? 5. The fuel economy of a 2011 Lexus car with all those features is normally distributed random variable with a mean of 22.25 miles per gallon and a standard deviation of 1.5. So notice it tells me what mu and sigma are. That's important. So I know what sigma is. I'm not estimating it. What's the standard error of x bar? The mean of the sample, random sample for 36 fill-ups by one driver. So we have number 5. They tell us that mu is 22.25, sigma is 1.5, and they want to know what the standard error of x bar is. What's the standard error? You have the standard error of an estimator. All that means is the standard deviation of the estimator. So this is just going to be sigma divided by the square root of n, and we're told that n is equal to 36. So what do we get here? We get 1.5 divided by the square root of 36, so 1.5 divided by 6. So what's that? 0.25? Is that right? Yeah. 0.25. Okay, within what interval would you expect the sample mean to fall with 99% probability? So this is part A. Part B says if the mean is mu 22.25, they want to know what are these values, mu plus z times sigma over the square root of n, and mu minus z times sigma over the square root of n, where we have 0.005 and 0.005. So the z values are given to us by I think it's a 2.575, something like that. We'll look it up for sure in just a second, but let's just plug these numbers in. 22.25 plus or minus, I believe it's 2.575 times 1.5 over 6. And we'll come over here to Excel and make sure we get that name, get that correct. So homework 6.5, we have mu, sigma, n, and alpha. So mu is 22.5, sigma is 1.5, n is 36, alpha is 0.01. How do I know alpha is 0.01? Because we're finding this 99% interval, so that means I've got 0.5% over here and 0.5% over here. Add those together and you get 1%. So our z value is going to be z sub alpha over 2. So this is norm dot s dot inverse 1 minus alpha divided by 2. Right, so this says give me the point that has 99.5% of the area to the left of it. That's the same as the point that has 5.5% to the right of it. So here's the 2.575. And so now for our critical values, or sorry, our lower limit, we have mu minus z times sigma over the square root of n. So 21.85, and the upper is going to be equal to almost the same thing. It's going to be mu plus z times sigma divided by the square root of n. So 21.85 on the low end, 23.14 on the high end. Let's try that again. So I guess we'll get different numbers. That's okay. All we have to do is change mu and sigma. So now mu is 20.5. Sigma is 1.25. Sample size is now 16. And our alpha level here has changed to 10%. 0.1. So that gives us different values. I don't know what happened with this, why it did what it did. We'll just check one of these. So we got the upper one right, which means we probably get the lower one right too. Okay, so what else we got? 14 and find the margin of error for a pole, assuming 95% confidence, and that pi is equal to 0.5. Okay, so for 14, what we're looking at is a confidence interval for pi, and we can write that down as p plus or minus z times the square root of p times 1 minus p over n. Actually, they're saying we should put a pi right here. That's the correct version of this, but we don't always know what pi is. So if we don't know what pi is, we need to estimate it somehow. And if we're doing a confidence interval, oftentimes we'll use p in place of that, but they're telling us in this question to use 0.5. So we're going to say, what's the margin of error? This is going to be p plus or minus the margin of error. So the margin of error is the z times the square root of pi times 1 minus pi over n. So let's come over here just to do the calculations. Homework 6.14. We have, let's see, alpha So 95% confidence interval. We've got n. And what else do we need here? Just pi. So pi is always going to be 0.5, n is going to change, and alpha is going to be 0.05. So for the first one, n is 50, and so we want, first of all, we need a z, so alpha over 2, so that's going to be equal to norm.s.inverse 1 minus alpha divided by 2. If alpha is 5%, we know this should be 1.96, close to that. And so then we finally have the margin of error, which is going to be equal to z times the square root of pi times 1 minus pi divided by n. Did I get the formula right here? So it's z times the square root of pi times 1 minus pi over n. So 0.13, or about 14%, is the margin of error there. And let's check that. I'm not sure I like what's going on with Connect right now. So let's try number 15. So we did get that right. The other ones just have to change the value of n. The z value? Yes, so we just want the value that has alpha over 2 to the right of it. So 2.5% to the right. That z value is 1.96. So we take that. Say, what's the point that has 1 minus alpha over 2 to the left of it? So it's 97.5% to the left. All right, number 15. Of 58 bank customers depositing a check, 23 receive some cash back. Construct a 90% confidence interval for the proportion of all depositors who ask for cash back. So number 15 says n is equal to 58, x is 23, and alpha is 10%, so and the sample proportion p is just x over n, which is 23 over 58. So the confidence interval, again using this formula, except for instead of pi we're going to use p. It's going to be p plus or minus z sub alpha over 2 times the square root of p times 1 minus p over n. So in this case, I'm not assuming that I know what sigma is. Since I don't know what sigma is, I'm going to estimate it with p. So just plug these numbers in. 23 over 58 plus or minus, what's the z value? It's going to be 1.645 times the square root of 23 over 58. That's 1 minus 23 over 58 divided by 58. So I'm going to come back over to Excel to do this. And I'm going to change this to homework 6.15. And alpha in this case is 10%, is that right? 90% intervals, so I'm going to change that to 0.1. Notice that changes my z value. And n is going to be 58. And I'm going to insert a couple of cells here. Move them over to the right. So here's x, and here's p. So So x is 23, p is equal to 23 divided by 58, and so we get 39%. And so I'll get rid of this. So the margin of error is going to be equal to, let's just delete this and start over. The margin of error is going to be z times the square root of p times 1 minus p divided by n. Right, so I'm just doing this in steps. So there's the margin of error. The lower confidence level, or confidence limit, is going to be equal to p minus z times the margin of error. Or, sorry, we already got the z in there, so let's just say p minus the margin of error, and the upper confidence limit is going to be equal to p plus the margin of error. So we have 0.5 is the upper one. Let's just copy that and paste it and see if we get it right. Okay, we got that. Part B, are we okay on that one? Just says, is it okay to assume that the sample proportion is normal? What is the assumption that what do we have to check in order for that assumption to be true? We have to have n times pi, or n times p, and n times 1 minus p. They both have to be greater than or equal to 5, I believe, what this textbook says. Does that sound familiar? It's either 5 or 10. Either case, we're okay because we have 23. That's bigger than 10. And 58 minus 23 is also going to be bigger than 10. So we should be able to say yes on that one. Questions on that? Oh, why did I do 15? Oh, because somebody asked for it. All right, all right. So we'll do 16 and then we'll do 3a. Did that out of order. I think that's okay. Okay, we got a 2009 Toyota 4Runner, all those specs. And we're told it has a normal distribution with a range from 12 miles per gallon to 18 miles per gallon. So this one's a little bit different than the last one. So the range is equal to the max minus the min, and the min is equal to 12, and the max is equal to 18. Alright, so estimate the standard deviation using method 3, which is the empirical rule for the normal distribution. So I believe that was a question on the midterm exam, actually. So we know that the range is equal to, or approximately equal to, 6 times sigma, according to the empirical rule. We've got the mean plus 1 standard deviation, mean plus 2 standard deviations, mean plus 3 standard deviations, so forth. And this has 99.73% of the data. So we're going to say the range is basically 6 sigma, and so sigma is going to be equal to 6 times the range, the range divided by 6. So in this case we have 6 over 6, so sigma is equal to 1. And the next part of the question says, what sample size is needed to estimate the mean with 98% confidence and a margin of error and an error of 0.25 miles per gallon? Okay, so that's probably the part you're having questions with, problems with. So we have a 98% confidence interval for mu, and that's going to be equal to x bar plus or minus z sub alpha over 2 and sigma over the square root of n. And this question is saying we want that plus or minus part to be 0.25 miles per gallon. We don't really care about the mean. All we want is the margin of error. It's going to be z sub alpha over 2 and sigma over the square root of n. And we want that to equal 0.25. We know what sigma is, we know what z is, or at least we can find it. The only thing that we don't know is n. So if we solve this thing for n, what do we get? We get n is equal to z alpha over 2 times sigma over 0.25, and I have to square all that. So that's going to give me, and all I did was solve that equation for n. That's going to give me what I'm looking for. So what's z sub alpha over 2? That's the point that has 1% of the area to the right of it. Turns out to be 2.33 times sigma, which is 1 over 0.25. If I square that, I will get to the right answer. So let's come over here. 6.16. What do we have? We have alpha. We don't have n. We're going to solve for that. We've got sigma, and we have the margin of error. So alpha in this case is 0.02. N is what we're going to solve for. Sigma is 1. Margin of error is going to be equal to 0.25. So what else do we need? We need z sub alpha over 2. And that's going to be equal to norm dot s dot inverse 1 minus alpha divided by 2. And there's the 2.33. Rounded 2 decimal places. So n is just going to be equal to the quantity z times sigma divided by margin of error and all of that squared. So 86.59. If I put in 86.59, I'm going to get this wrong because sample sizes can't be fractions. So I'm going to round up. I always round up in a situation like this. If I don't round up, if I take 86 instead of 87, then I'm not going to have 98% confidence, or I'm not going to have the margin of error that I specify. So this is overkill. This is a conservative thing to do. But you always want to round this up, not regular rounding. Always round it up, even though that does round up. Okay, so the last one that we've got is number 3. A poll of 2,291 likely voters was conducted on the president's performance. Approximately what margin of error would the approval rating estimate have if the confidence level is 95%? Okay, so we want to know what the margin of error would be. So margin of error is the p plus or minus. Margin of error in this case is going to be p plus or minus square root of pi times 1 minus pi over n. Now I don't know, again, I don't know what pi is, but I also don't know what P is because I haven't taken the sample yet. So if I have to estimate pi, worst case scenario, the biggest, are we looking for margin of error? Okay, so we have n. Let's write that down. N is equal to 2291. If I don't know what pi is and I don't have some sort of estimate for pi, then I use 50%. Because if you take a look at what this, if you take pi times 1 minus pi, what does that look like to you guys? Think algebra, think quadratics, quadratic equations. It's pi minus pi squared, which is a quadratic that looks like this. So it's going to have a maximum value at 50%. So the most conservative thing to do is to use 50% in this situation. So we're going to plug that in here. So our margin of error is equal to the square root of 0.5 times 1 minus 0.5 divided by 2291 times z. And what's our z in this case? 95% is alpha, so z is going to be 1.96. So alpha equals 0.05, so z is 1.96. So I'm going to come over here. Homework 6.3. What have I got? Alpha. I've got n, and I've got pi. So alpha is 0.05, n is 2291, pi is 0.5. Now they didn't give me that 0.5, but that's something you have to learn. Use 0.5 if in doubt. And so then z of alpha over 2, that's equal to norm dot s dot inverse 1 minus alpha over 2. So the margin of error is going to be equal to z times the square root of pi times 1 minus pi divided by n. So it's about plus or minus 2%, which is pretty standard for political polls. This is what they always shoot for 2% with a 95% margin of error. Okay, part B just says put 0.46 in instead and use that. So, but they also want the interval, so you have to come over here and add to that. .46, although that's not really pi, is it? Let's change that. Let's say we have p 0.46, and I won't plug all this in, but that's the same thing as what you did up here in this one. So if you put it all in the same order, it's the same function calls as that, which means I should be able to copy it and I'll paste it right here. So again, alpha in this case, so I guess I will do this for you. Alpha is 0.1, n is 2291, x is I don't actually know what x is, but p they told me is 0.46. So that should work out. I'm not going to double check the formulas, but you can go back and check that out if you like. So let's just check this one, make sure we got that part right, and we did. All right, so no other questions. Then I'll see you guys a week from today, and that will be our 9th meeting, and then we have one more after that.